Is the worksheet accessible? Good question, guys. You need to figure out it, because for me they are accessible. I will just check it one more time. Okay, interesting. It's ground lesson 11. They were switched. We changed the order. Okay, nice. Wait. Now I cannot. Because the caps lock. Yeah. Okay, for Duncan it works. It also works for me. It also works. Okay, 25. Let's wait. 0.5. Two more minutes, just in case. And then, Jeremy, I'll send to you the worksheet for the ground lesson 11. So yeah, that's the worksheet. Should be accessible now. Try it. If it works. Okay, good to hear that. So let's start then. Today's class: information on charts and airspaces. The lecture is divided into two parts. First one is general theory, also related to general navigation. We will figure out how the charts are built, what are the principles, how to work with the grid coordinates, where it originating from. Second part, which will be on Monday, more practical. I mean, this here also practical application. It's not like there will be some theory at the beginning, but then we will switch to practical things. Just on the second half of the class, which will be on Monday, we will speak more about the airspaces as airspaces, like classes of the airspaces, the rules applied in these airspaces, some speed restrictions, whether you can enter or not. Today we will discuss how the charts are created, what is the background behind, and how to, based on that information, how to work with them. Okay, so I need to share the screen. Just a second. So it should be visible, yeah? Write me.
Yes.
Okay, cool. Good, so let's start then. As we depict on the charts, we depict what contains on the Earth. Let's make an intro about the Earth. What is the Earth? What is the shape of the Earth? Well, there are two approaches of defining the shape of the Earth, like what is its actual shape, and another approach is the shape which is applicable for the calculation. Exactly, flat. That is the secret that I wanted to reveal. Yeah, this is all only in flight schools. Okay. Of course not. It's not flat. It's rectangular. No, I'm joking. So the actual shape of the Earth is referred to be geoid. How that was yesterday. Where it was yesterday. The class was yesterday. April Fool, exactly. Yeah, so the geoid is the actual shape of the Earth. There is no synonyms. It is geoid. So this spherical shaped body, however, it's not a perfect sphere. Yeah, it has impurities. It has shapeless distortions, let's say. Yeah, of course, those the hypsometry that you can see here on this rotating image are over exaggerated because the highest difference in height across the planet is Everest is 8 kilometers, yeah, approximately, and Marianne Crest is 11 kilometers. And however, we don't know about the rest of the ocean floor, so there might be some deeper parts. I mean, among known is the difference is approximately 20 kilometers, which is nothing. However, still, it's not perfect. Plus, it has some it has other forms of impurities, imperfections. So this geoid is something that we don't want to work with because it would be very hard to establish the some common reference. Yeah. So as it often happens in aviation, we round the things up. We say, okay, let's make it more or less practical, some geometrical approximation. What will be the closest figure in terms of the geometrical approximation? That would be a sphere. Yeah, so for most navigational purposes, the Earth is considered to be a sphere. However, even this is also another approximation. Yeah, in fact, it's something which is called oblique spheroid. So this is the sphere which is slightly flattened on the poles. Along the equatorial part, it's a bit extended and flattened at the poles. That's happening because the Earth rotates and centrifugal forces, they stretch the Earth in this equatorial plane. However, this flattening, or sometimes it's called compression, is not significant. Yeah, it's only like 0.3%, which gives you the difference in approximately 43 kilometers in circumference across the pole in comparison to the circumference across the equator. And for PPL stage, it's good if you know that. However, like such deep details are not required. For ATPL, yes. For ATPL, you need to know that. You need to know the figures. But now it's just telling you that for most navigational purposes, it's considered to be a sphere. So if it's considered to be a sphere, then we can do some manipulation with this sphere. Those manipulations are, which are not even quite manipulations, but within any sphere, we can fit circles, different circles. First type of the circle is the circles which have the center of the circle, which is coinciding with the center of the sphere itself. So as you can see here on the slide, circles whose center and radius are those of the sphere itself. Yeah, basically what I said. In this case, we would call these circles great circles. So these are the great circles. And this is the definition. How else we can imagine this great circle? You can just take the Earth, and if you would have giant piece of paper, you will just slice the Earth in half. So like it's shown on this picture, and this area where this paper is cutting through the Earth, this circumference would be a great circle. That would be the, and meaning that this paper cuts through the center of the Earth, of course. So this is the great circle. Next, later on, we will come back to this great circle. But now I will say also, on any sphere, the arc created by this great circle would be the shortest distance between 2 points, like as you can see here, A and B. So that would be the shortest distance between A and B. Great circle would be the shortest distance. Another type of the circles that we can fit within the sphere, the circles whose center and radius are not that of the sphere. So, and that would be as shown on the picture, this circle, small. We will call them small circles. And it actually, this is the official naming of such type of circles. So great circles cutting through the center, great small circles are not. Here is the generalization slide. Okay, it's not hard. So next one, where do we use these great circles and small circles? Where? So aeronautical application of the small circles. With the small circles, we measure the parallels of the latitude. Parallels of latitude are small circles which are parallel to the plane of the equator. So here you have it on the slide. These are the small circles, parallels of latitude. Equator itself is also parallel of latitude, but it is a great circle because the equator itself, the circumference of the equatorial circumference, has the center at the center of the Earth. So this is one exclusion from the rule. All the others, parallels of latitude, small circles. Then aeronautical application of the great circle, except for the equator, as we said. With the great circles, we denote the meridians, or sometimes called longitude. And here you have it on the picture. So these are the great circles. What these parallels of latitude and parallels of and longitudes, meridians are used for. Let's start with the general. First of all, they used for creation of the grid of the Earth, because this parallels and latitude and meridians, their intersections. Yeah, by their intersections, we may measure some position. We may define the position. Also, I wanted to say that, okay, that would be later. So they form a network on the globe that we used for defining the positions. The network is used is created by referencing to two datums. First datum is the prime meridian, which is sometimes called the Greenwich meridian. Maybe you heard this. And the equator. So on the one side we have prime meridian, Greenwich meridian, and the equator. So this is your reference datums for the graticule. We calculate all the latitudes, longitudes from these two references. So this graticule, as you can see, it's written on the slide, is an analogy of the Earth surface, like XY graph. You know, this when you draw on the paper, like standard mathematical graph. So, and then you calculate correspondingly from one axis or from another axis. So this is this analog. The prime meridian, Greenwich, divides the Earth to the Western and Eastern hemisphere, as it's shown on this second picture on the right. Yeah, the rightmost set of pictures. And the equator divides the Earth into the northern and the southern hemisphere. So as the result, we have like four pieces. And consequently, the directions are also stated in reference to this graticule. Yeah, we have north, we have south, we have west, we have east, we have northeast, we have southeast, southwest, and so on. So this is, everything is coming from this graticule. How do we measure the positions? Yeah, because we said that it's used to measure the positions. The positions are measured in the following way. So first we need to determine the unit of measurement. Yeah, how do we measure the positions? Normally on the circle, on the sphere, we measure the angles. We measure the angles by using the radians. But radians are inappropriate for navigational use. Yeah, this is just theory. Normally we use with the radians. Yeah, 1 radian is the arc which has the length of the radius itself. But circle has approximately 6 radians in it. This is not enough. That wouldn't be very precise if we would have only 6 steps, you know, in measuring the whole Earth. So we have reverted to degrees. So instead of radians, we use degrees, where the whole circle will be 360. Consequently, half of the circle would be 180, and the quarter would be 90. Now, how this applies on the Earth? Before this, I want to also mention that degrees are also not enough. It's also not enough for us. We need to go further. So after the degree, each degree can be divided to minutes. And then each minute can be divided to a second. The logic is the same as with the hours and minutes. So we have, let's say, we have hour. The hour is composed of the 60 minutes. Each minute is composed of 60 seconds. Here is the same. 1 degree is like 1 hour. Then our degree as hour is divided into minutes, and minutes divided into seconds. So basically, degrees, minutes, seconds. Each of the following is the stands for 1/60 of the previous unit. So as with time analogy. I hope that's good. So, measurement of the latitude. So since we now know the units of the measurement, which are degrees, minutes, and seconds. So how do we measure the latitude? So let's start with the latitude. Yeah. Latitude, we measure parallel. First of all, parallels of latitude lay in east-west direction, but they indicate the position north or south in respect to the equator. They lay in the east-west direction because they form the circumference around the Earth. So if you will move along the latitude, so you will go either east or west. But the latitude itself represents whether you north or south from the equator. Yeah, like just refer to this. Just refer to this picture. Yeah, this white. Okay, here's your latitudes. They lay in east-west direction, but they show you whether you are north or south from the equator. So we measure those latitudes referring to the equator itself. So we basically take the angle. We take the angle between equatorial plate and your current latitude, so where you are standing on the Earth. And here's how this angle is measured. It's shown on the picture. Yeah. So this is your reference. The equatorial plane is your reference, and then let's say here's your position somewhere north, yeah, of equator. You put the straight line to the center of the Earth from your position, and you measure the angle between these two lines. So this is how you define your latitude. Because latitudes, I mean, don't think that latitudes are. What is the maximum amount of the latitude? The maximum amount of the maximum value of the latitude is 90 degrees. Yeah, because you may have maximum 90-degree angle with respect to your reference, which is equator. Yeah, once you reach 90 degrees, that would be top of the Earth. Yeah, it's not really precise wording and not accurate, but as to simplify the things, as shown here, yeah, on the picture on the right, you will reach the North Pole. So this is maximum. If you will go more than 90 degrees, you would be just on the other side from the North Pole, and still there would be some latitude which is less than 90 degrees. So maximum amount, maximum value for the latitude is 90 degrees, and the minimum is 0. Where 0 is equator, 90 is the North Pole. However, don't think that there is only 90 of those latitudes, because you can effectively divide endlessly. You can always find some smaller fraction. Yeah, you can say, for example, latitude 45 degree north, or 45 degree 1 minute, 45 degree 1 minute and 1 second. Yeah, so each position on the Earth, wherever you are, there is some latitude coming through. Just it has unique value, unique numerical representation. So don't bound yourself to only 90 degrees. Yeah, there is always something in between each degree, because it can be divided further and further to minutes, seconds. So 2 people standing 1 meter apart will have effectively different latitudes running through them. So one more time, the picture that shows you the measurement of the latitudes. 0 is the equator, and then 15-degree angle, 30 degree, 45, 60, 90, North Pole, and then if you will go further than the North Pole, 60, 45, 30. Yeah, you just go to the opposite side of the North Pole. Okay, I hope that's clear. Measurement of the longitude. How does this happen? The longitude is measured in respect to the Greenwich meridian. So again, your third. Okay, sure. Just I beg my pardon. Just 1 second. I'll be back in 15 seconds. Okay. So yeah, you're welcome. Now the longitude. Longitude. How do we measure the longitude? In respect to the datum for the measuring the longitude, the datum is the Greenwich meridian. So the Greenwich meridian is what is this? It was created. It was named as the reference. Just historically. I mean, if with equator there is at least some sense, yeah, why equator is the reference, because it's the geographical center between North Pole and the South Pole, and it's in ideal model this is the thickest part of the Earth because of the spinning, rotating forces. It has some sense, but with longitude, like any longitude can be a datum longitude, because the Earth, the sphere is uniform from no matter from which side you are looking on it. So the Greenwich meridian was selected as the reference just purely historically. There was in England there was a Greenwich observatory that was making some scientific observations, yeah, of our planet, and it was named after it. So it's basically this Greenwich meridian is located close to London. Like I don't remember exactly, 30 kilometers or 30 miles, or maybe even less, like really close to London. So yeah, this is the Greenwich meridian, and from this meridian we measure the angle to our. Yeah, for sure. It's now also important for any navigation, because this is the basic. This is how you create some system in where you can measure the coordinates are important, because you need to say your position and how would you refer to your position. I'm let's say next to this island. Where next to this island? Yeah, or east to this island. East in respect to what, and where the east is coming from at the first place. Yeah, so this equator and Greenwich are the basics to in creation of these references. So and again, and longitude is the angle measured between observer position, where you are standing on the Earth, and the Greenwich meridian. Following the same logic, yeah, you have Greenwich meridian. Imagine that it cuts through the center of the Earth, like the whole plane. It cuts through the center of the Earth. Then your position, you also located on some point of the great circle that cuts through the center of the Earth, and then you measure the angle between them, as shown here on the picture. Or that's another picture that basically shows the same. And for example, as you can see here, the angle is measured 60 degrees to the east. So we will name this longitude 60 east. This is how the longitude named. The same latitudes are also named. If you will measure to the north, let's say parallel, latitudes, yeah, parallel 30 north, longitude 60 east, and so on. If we if with the latitudes we had the limit of 90, you cannot have latitude more than 90 degrees. Yeah. With longitudes, we also have a limit, and this limit is 180. Because once you are passing 180, you will get into another hemisphere. That's reference into this one of the first slides where you had east and west hemispheres. So the maximum amount of the longitude is 180 degree. There is no longitude 220 degree west. If you have longitude more than 180, you are already in another hemisphere, and you just need to look at things from another side, from another angle. So longitude to 220 west would be actually 150 east, because 210 is 30 degree more than 180, but we cannot have more than 180, so we need to subtract actually and change the designator if we were counting through west. We will pass the border and we will get into another hemisphere. Also note how the longitudes are named, like the reference longitudes, the prime meridian and its anti-meridian. Yeah, it's called 000 degree west east because it's zero, it's neither west nor east. And on the other side, you have 180, also west east. All the rest are either west or east. And also, what I wanted to tell that, okay, maybe it will be on the another slide. Okay. So defining the position of the Earth. So as I said before, we hold this idea of having this longitudes, latitudes, longitudes, and degrees to define certain positions. So by using these longitudes and latitudes, we can define pretty much any location on the Earth. For example, this Ruzhny Airport. Yeah, let's take as an example. This is the picture from the VFR manual. Yeah, it says that it's located at, and here are coordinates. Yeah, you see here, airport, APR abbreviation, 50 degree 6 minutes and 3 seconds north, 14 degree 15 minutes 36 seconds east. Yeah, these are, by the way, the is it good visible for you, because these are the signs for degrees, minutes, and seconds. So degree will be like the degree symbol. Degree symbol, minutes would be 1 short dash, and seconds would be 2 short dashes. 50 degrees, 6 minutes. APR stands for airport reference point, aerodrome reference point. Each airport, I mean, if we need to measure the location of certain point on the Earth, yeah, it's easy if it's just the point. However, what if we need to state the coordinates of the whole airport? Actually, that's actually the good question, because remember before I said that don't bound yourself that to, you know, to degrees. There is always some smaller fraction that you can specify to. So the airport is occupying some space on the planet. So different parts of the airports technically would have different coordinates. One threshold and threshold which of the same runway, which are 3 kilometers apart, would have different coordinates. So in aviation, if we want to measure the location of certain item, that we would have to establish some reference point. For airport, this is the airport reference point. It can be found on the chart. I can actually show you, why not, since this is about the airspaces, and we've been asked this question. I'll show you where to find this aerodrome reference point where it's located. So EASA. We need briefing. It can be done via VFR manual. It can be done via AIP. Later on, I will show you which of them are standing for what. So I just need to find Rosinia, Lima Kilo Papa Romeo is the abbreviation. Lima Kilo Papa Romeo and aerodrome chart. Now I need to scale this up. Here is the aerodrome reference point. So the center of the Rosinia airport is on the runway, is located on the runway 3012. So you see this is where the center of the Rosinia is measured from. Okay. Let's continue. Actually, also speaking about defining the coordinates, here is nice animation. How does it? So let's say we want to define the Rosinia airport. Yeah, so Rosinia will be located. Its coordinates 14 degrees east, 14.5 approximately, and 50. Let me refresh myself on the knowledge. So coordinates 50 degree north, 50 degree north, 14 degree 15 minutes east. 1450. So 50 degree north. So somewhere here, 50 degree.
So is the minutes and seconds just the decimal points?
Yeah. Yeah, here in this application, yeah, we can change to minutes and we can change to minutes. Seconds are normally not used in, it's rarely used in aviation because, I mean, they are used normally. They used, you saw just now, you saw the coordinates of the airport, the seconds are there. However, for you as the private pilot, you will barely use seconds because you don't need this precisionness. We will now speak about the distances which represent how many degrees, how many nautical miles is in 1 degree, in 1 minute, in 1 second, and you will see that normally seconds are omitted because it's very most of the time very unnecessary specification. So yeah, 50 degree north, 14 degree east, 14-15 minutes. Yeah, so somewhere here. Okay, I don't want to take a lot of time to. It's unnecessary here. But I hope you get the logic. Yeah. So here I'm transferring to Western Hemisphere. This is the Greenwich meridian. Here again in Eastern Hemisphere, Western, Eastern. Now I'm in Southern Hemisphere, moving southeast. In Northern Hemisphere, moving northwest. In Southern, moving southwest, and so on. I think this animation is pretty self-explanatory. about conversion between this decimal and decimal representation of the coordinates and minutes and seconds. In case you will have to use this conversion, 60 seconds is 1 minute, and that would stand for 1 nautical mile, but later on. In case you will have to convert on your exam between minutes and decimals, so the logic is simple. You need to, since each of the following unit is 1/60 of the previous, you need to divide by 60 in order to get the representation of the previous unit. So let's say you had 25 degrees and 14 minutes. If you want to write it down in degrees solely, you need to take this 14 minutes, divide them by 60, and that would be, let's check. I mean, I know that I can switch the numbers, but let's check on the calculator how much it will be. 14 minutes divided by 60 is 23. So 0.23. So this is 0.23 degree. 14 minutes is 0.23 degree. So in this case, if I'll take this latitude, 25 degree, 14 minutes, and convert it to decimal, I should get 25.23 degree. Yeah, 0.2. Okay, it's abbreviated. But you got the logic, yeah? How to convert between decimals and specific and minutes and seconds, because sometimes some questions actually, this is rather from the GNAV, but I can show you now, because on GNAV we'll not have much time to go through these details. But airspaces is, this chart section is exactly good time to go through this. So let's say we have 16 degree, 23 minutes, and 30 seconds. So since seconds are not used normally in aviation, again, from practical, from your private pilot application, so we can write this number in degrees and minutes only. For this, we will have to divide this last seconds by 60. We will get 0.5. Yeah, so we will write down that these coordinates can be stated as 16 degrees, 23.5 minutes. Makes sense, yeah? It's like 2.5 hours. It stands for 2 hours, 30 minutes, yeah? So the same here. 2.5 degrees would be 2 degrees, 30 minutes, yeah? Because we take this and multiply by 60. So that logic of conversion. Clear, guys?
Yeah.
Okay. If not, just let me know. We'll go more detailed. Okay. So this is how we define positions. Now to the concept of the orthodrome and the loxodrome. That would be related to great circle and not great circle. That would be most correct formulation. On Earth, we can, there are two paths between point A and point B. So first is the orthodrome. and orthodrome is the part of the great circle. And another one is the loxodrome. The loxodrome is called the rhumb line. You can write this down because so you will not confuse yourself later on. So we have orthodrome and loxodrome. This is how we can get from point A to point B. So and here they are on the picture. So from this picture, what we can say? We can say that orthodrome, or the great circle, as we mentioned before, would be the shortest part between shortest route between point A and point B, because Earth is considered to be a sphere. On the sphere, the great circle is the shortest part between point A and point B. So the same on the Earth. Great circle would be the shortest path, and great circle is the orthodrome. And then we have the loxodrome, the rhumb line. So the rhumb line will not be the shortest path, but why do we use this at all? Actually, we don't use this like in majority of aviation does not use the rhumb line. The rhumb line is the only advantage of the rhumb line is that this is the line between 2 points that cuts every meridian at the same angle. So here you have your meridians. Yeah, we know that meridians are going from the north to south pole. Yeah, where's my pointer? So the meridians are going from the North Pole to the South Pole. These are meridians, and we measure angles in navigation in respect to the no, Jeremy, that would not be very correct. It's not the correct wording. Cuts. First of all, it not cuts. Yeah, it just circumnavigates around the Earth's surface. Then it runs along the same latitude. That wording may be correct. However, the rhumb line is not necessarily laid down parallel to the, like, it's if you have 2 points which are located on the same latitude, then yes, you can say like this. The rhumb line will be just along one latitude, but those points can lay in at different latitudes. Yeah, for example, if not Moscow and Vancouver, but take Vancouver and Dakar. Dakar will be somewhere here, and even though there still will be a path which will give you the same angle, I mean the same direction, it will not lay along the same latitude, because Vancouver and Dakar are at different latitudes. So you cannot go from Vancouver to Dakar along the same latitude. But you can go from Vancouver to Dakar with the path which is cutting all the meridian at the same angle. And that would be the rhumb line. However, it would not be the shortest path. It would be just the path which is convenient for plotting. Yeah, you will plot the route. You don't have to think. You just put the straight line. You draw from point A to point B on the map. It gives you the same angle along all its way. But from practical application, it will not work. I mean, it will work. You will eventually reach there, but you will use more time to reach there. So the great circle will, however, but great circle changes direction constantly. And this is the disadvantage of the great circle. So the disadvantage of the rhumb line, that is longer, the disadvantage of the great circle, that it constantly changes the direction. However, I mean, you shouldn't know how to calculate the direction of the great circle on the PPL, but I mean along your route. But again, it's good that you know, you should know the difference between them. Let's say like this. So this is the orthodrome, as we already mentioned. Yeah, because here is the example, Jeremy, where the point A and point B are not laying at the same latitude, and still there will be the line which is the shortest distance, and that would be the orthodrome. However, in reality, it will never cut at the same angle. Because remember this example with the slicing earth with the flat piece of paper. Yeah, so you can say that the line that connects point A to point B is the straight line, but it goes underground somewhere, and you cannot. But we cannot fly underground. We need to fly the projection of this straight line along the curved surface of the Earth, and this is why this projection would be this would appear to be curved. It's actually a straight line, but because the Earth is sphere, it appears to be curved on the map. However, in reality, this is the straight line. One more example of the great circle. That the great circle is always shorter than the rhumb line and small circle if by chance those coincide, rhumb line and small circle. So for example, we have we need to go from Boston to Shanghai, and this white curve is the great circle. Yeah, because imagine that the center of this white circumference goes through the center of the Earth, and this is the small circle. Since Shanghai or Beijing, okay, and Boston are approximately at the same latitude, we can use the approximation. We can use as approximation. We can say for the approximation purposes that this small circle corresponds to the rhumb line because it almost cuts every meridian at the same angle. Yeah, because it lays within one latitude, at the one latitude approximately. So, but if we will look from the top on this picture, yeah, that here we clearly see that, for example, to go from Toronto or Boston, whatever we had there, from Toronto, yeah, to Beijing, along the small circle would be much longer route than go via the great circle. Yeah, the direction will not change. You will technically all the time fly, let's say, 090 degree east. Yeah, all the time to the east. But you will have to travel all around the parallel of latitude. But if you will go along the great circle, yeah, the direction would change dramatically because you will first go to the north, and then you will basically go to the south. When you will cross the North Pole, you will go to the south because you reach the north. There is no more north after reaching north. If you continue going straight after north, you are going south. From North Pole, there is all directions are the south actually. So this is as an example. Yeah. Okay, here we discussed this. Why the great circle doesn't look as the straight line on majority of the chart? That is about the projection. We will speak about this in a couple of slides. And for now, and here is the slide, the example that Loxodrome, the rumb line, you can also connect 2 points which are not at the same latitude. But again, that wouldn't be shortest distance. And actually, if you fly along the rumb line in any direction except strictly to the north, or strictly to the west, or strictly to the east, you will, with the spiral, in a spiral manner, you will sooner or later reach the North Pole. Actually, you will never reach it because you will always rotate around. Yeah, it will lead you towards this northern region, and it will keep spiraling endlessly to some Planck lengths, but will never reach the North Pole. And this is how the mathematics work. Here is the difference between Loxodrome and the orthodrome one more time. Great circle distance, shorter, and rumb line. This one is clear? Okay. Now, speaking about the great circle. Speaking about the great circle, basically we said everything that, yeah, the great circle changes the direction. So yeah, here is the bunch of slides that are just showing you how the great circle changing the direction and how rumb line doesn't. And the question why something which is shorter appears to be longer when is written, when is drawn on the picture, that is about the projection which we are used for the chart composition. And here is actually the spoiler here in upper right part, the Mercator projection. So on the Mercator projection, yeah, you really have this type of distortion. How this projection is formed, we will soon speak. Okay. Projections. Yeah, so let's go to the projection. The projection is as the slide suggests us, that is the result of the transferring of the information from the globe on the flat plane. However, there are problems with that. There are problems because we have developable surfaces and not developable surfaces. For example, cylinder and cone are developable surfaces, and we can develop them to the straight piece of paper, which is the chart. But Earth is the sphere, and orange, for example, is the approximately sphere, and you cannot just make it straight. You will have to break it. You will have to ruin the structure. So this is the first problem that we reach on our way in forming chart. This is, however, figured out mathematically. So there are mathematical models how we will unfold the spherical Earth to the flat plane. For this is scientists will take care of. Then we have another problem with depicting projecting the Earth on the paper. It's the distortion, which is called by the perspective, and this is already cannot be fixed by the mathematicians. So here we need to make variations. We need to select which projection would be most favorable for us in composing the charts. We have three main projections: cylindrical, conical, and azimuthal. Each of them are good for certain cases. So which are those cases? Let's see. So in the but before, yeah, okay, but before, what would be the ideal chart projection? Yeah, we have three of them, but what would be the ideal? The criteria that we set for the projection is that the directions would be true. What does it mean? It means that, let's say, if we measure if in reality you measure the direction to some hill, and it says that the direction to this hill is 050 degree, then you want to make sure that you will measure the direction on the chart, and it also will give you 050 degree. Yeah, normally directions are measured in reference to the north, and the north is just the direction towards along the meridian. Yeah, direction along the meridian is towards the North Pole is the north from where we measure. So if you measure this in reality, then you of course want that your chart will have the same properties. So this is the first. And the second one, distances would be represented at the constant scale over the entire chart. So what does it mean? That you will not have any distortions at any position on the chart. Well, let's say you have chart of the world. You want to have such a property of this chart that you measure the distance close to equator. You know the ratio of the chart, let's say 1 to 500,000. So you measure 5 centimeters, and you know that this is, let's say, for example, 20 kilometers in reality, yeah? And you will measure the same 5 centimeters on the chart close to the pole, and it will also correspond to 20 kilometers in reality. So we would like to have these properties. However, we cannot. Because of the different actually reasons. But these properties we would be able to attain only on the globe. I mean, we will always have some distortions caused by the projection. Specifically, it is related to the second parameter, that distances would represent at the constant scale over the entire chart. Unfortunately, no, they will not. And this is one of the considerations when we create the charts, which type of the projection we use. Later on, I will return to this. But okay, since we cannot attain the best characteristics that we mentioned before, what we can expect, at least something we can expect from this chart. Yes, at least something we can. And these are thank you. Okay, let's yeah, okay, you know, guys, let's make a quick break. Actually 15 minutes break. Yeah, I need to also, my student have returned from the flight. No problem. So and we will continue. Okay, let's make it 15 minutes. Yeah? Ciao, 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 ciao. So, okay, my student, there was a first solo navigation. He successfully returned. Now I'm 100% back because I was thinking about this. First solo navigation. And yeah, okay, good. Yeah, he did well. Everything was good, and now I'm happy. And let's continue. So aeronautical charts. What? Okay, we cannot achieve this ideal properties. We cannot. No, he returned. Yeah, I expect, of course, all the time, everyone. So we cannot attain perfect properties. We cannot have the constant scale on the chart. It will always have some distortion. We need to select appropriate projection in order to eliminate this distortion to the minimum. But something we can ask from the chart to have, and this something is ability to use coordinates to identify positions and features. For sure, we need to have grid on the chart. We need to have these coordinates. We need to have, not coordinates, grid, latitude, longitude. That should be there. Very soon, I will tell you. I'll reveal you the secret which projection. Lambert, but what is Lambert? Yeah. Condition number one. Condition number two. Condition number two, geographic positions and features should be easily identified. Exactly, which Lambert? Conformal conical Lambert, but step by step, we'll get to. Geographic position of features should be easily identified, for sure. Why do we need the chart where we cannot identify the features? What is the use of this chart? That's not good. So it should be there, and it's there. Ability to use positions and features to identify coordinates, vice versa. Because if you landed somewhere, this is example from my mind. If you landed somewhere and you can identify the position where you landed by chart, that okay, I have the city, I have the chimney, I have the lake, but where am I exactly? For example, you need to send the coordinates. Then by using again the grid on the chart, you can check with this grid. Okay, I'm 53 degree north, 14 something east. So this is my coordinates. It should have constant scale, and I just said that constant scale we cannot use, we cannot have, but I said we cannot have it all from like globally, but at least within usable portion of the chart, we need to have more or less constant scale. So it will not be constant, but it will be usable enough. The tolerance will be adequate to use this chart for navigational purposes. And another condition, straight line drawn on the chart should approximate great circles. Yeah, that would be very useful, especially for the VFR charts. They should approximate great circles because the rhomb lines, we are interested in flying great circles. It's not the main thing of this. It's rather like more towards ATPL subject why it should approximate great circles, but it comes from the part that we use very limited portion of the projections. So in 2 or 3 slides, there would be a slide about this. The chart should be also orthomorphic or conformal. What is this? All those previous are more or less items are understandable as they are. But what is the orthomorphism and conformality, the property of the chart that chart has to attain. So in order for the chart to be called conformal, the following criteria should be met. So the navigation bearings must be correct. And this is from the slide before the previous one, that the angles on the Earth should be measured on the Earth, should match those angles which are measured on the chart. So this is condition number one. And it is the main condition. And in order to achieve this, the meridians should be straight lines and intersect parallels of latitude at the right angles as they do on the Earth. Because in reality, yeah, they always intersect at the straight line. So this is the criteria to the chart. It should be conformal, so bearings would be correct, angles measured would be correct, and all those previous items that we need to able to distinguish features, identify positions by using coordinates. So these are the criteria. Now, which types of the projection do we have? We have first one is the azimuthal projection. So the azimuthal is type of the projection is that type of the projection in which points on the Earth are transferred directly to a plane tangent to the Earth. So basically, you take a sheet of paper, you put your reduced Earth next to it, and then it's normally done with the, I mean, of course, nowadays it's done mathematically, but before, it's done via the source of light. Depending on where you will put this light, you will have slightly different projections. It can be point A, point B, or point C. Point A is called gnomonic from the center of the Earth. B is stereographic from the diameter distance. Yeah, so here's where is B. And orthographic is from the infinity. In aeronautical application, the stereographic is used. The stereographic type of the projection is used in the azimuthal projections. However, there is very limited applicability of that type of the projection. This limited applicability originates from the fact that when you will have projection like this, you will have big distortion. Let's say whatever is tangent to this sheet of paper will be represented correctly on the sheet of paper, but points, let's say somewhere aside from the tangent point, would be represented with a distortion. So for this type of the projections are used only in projecting in polar navigation, in projecting poles. So because of this, the name of the projection is the polar stereographic. So stereographic because of the type of the projection itself, yeah, like this azimuthal stereographic projection, and polar because normally it used to depict the poles. So here is how it's done. Yeah, you take a sheet of paper, let's say some plane to which you would project. The tangent point is the pole. Then the source of light is originating from the opposite pole. You project it to this plane. As the result, you will have this picture on the right is the resultant, what you would have. And the problem with this that you will almost not have distortion at the pole, but you will have a lot of distortions anywhere else. And because we said that distortions in projection are causing distortions in scale, because it will be hard to measure the scale from this type of the projection, because there will be no uniform scale across the projection, because let's say 1 centimeter on this projection next to the pole will represent certain amount of the distance on the Earth, but on the other side, 1 centimeter somewhere here will not already represent the same amount of the distance at the Earth, because the scale will be not constant. So this is used only for polar navigation. As long as we are, guys, not flying in the North Pole, you can just know that this projection is present. It's not used worldwide because of the big distortions caused by the scale distortions. However, it's present. And on PPL, they ask what the types of the projection. So you need to know that there is a polar stereographic. Polar stereographic projection is actually used as the logo of the United Nations. Who was mentioned in the flat Earth, because this conspiracy theory, one of the arguments in this conspiracy theory that, come on, even United Nations depict the Earth as the flat plane. No, it's just the azimuthal projection of the North Pole. Yeah. So, okay, this is the azimuthal polar projection. Another type of the projection is the cylindrical projection. And the most famous among this cylindrical projection is the Mercator. So how it's done? It's constructed by putting the Earth into the cylinder, within the cylinder, and then the light source is within the Earth itself, in the center of the Earth, and you project sidewise. I mean, you project from the center of the Earth towards this flat plane, and this is the only projection that will give you the rhomb line, on which the rhomb line will be represented as the straight line, because rhomb line cuts all the meridians at the same angle, right? And here meridians are all parallel. So if you, in geometry, it's the law of the geometry. If you have parallel set of the parallel lines and you draw the straight line across them, it will cut all the lines at the same angle. So the same is here, and rhomb line exactly cuts all the meridians at the same angle. So this is why normally the rhomb line on majority of the charts will look a straight line, because the majority of the charts you saw before coming to aviation were not aviation type of the charts, and they were atlases, they were for some books. Those normally for the projections to the walls, you know, like when decorating the room with the map of the Earth. Those are normally Mercator projection. I don't know if the Chrome key is on, but apparently, yeah, behind me it's also Mercator projection. But it's not the projection that is used in aviation, because it gives the huge distortion, and this distortion can be seen by this picture. I mean, you most probably heard that Greenland is oversized on the map. Why? Because of the distortion of the projection that is normally used for non-aeronautical charts. Yeah, so because this is the actual position on the chart, but if it would be located where the USA located, that would be this size, and on the equator it would be this size. In Mercator projection, the scale is not distorted next to the along the equator. In polar projection, the scale is not distorted over the pole. In Mercator projection, classic Mercator projection is not distorted along the cylinder. We can make a conclusion from it that the projection does not have distortions at the place where the projection touches the reduced Earth, yeah, where it touches this globe. Like on pole, it was touching the pole, there was no distortion on the pole. Equator, the Mercator touches the Earth of the equator, there is no distortion on the equator. But elsewhere, it is distortion. So, and because of this, we don't use this in aviation. Because it would be, I mean, you would have to move this cylinder, but you cannot move cylinder in a manner like you can tilt it to the side. You can wrap it over the pole, but you will never get a satisfactory result to depict, let's say, for example, I don't know, Germany. Yeah, Germany is spread both northeast, north, south, and west east. Yeah, so it's impossible to cover whole Germany with only one tangent point, as this Mercator projection gives you. So it's not used in aviation. Actually, there is a, I think this is the next picture. If we would use the Mercator projection, yeah, to, if our Earth would be the sphere with the face depicted on it, if we would use Mercator projection, this is what would happen with this face. So you see the magnitude of the distortion. However, it's used for non-aviation types of the charts. And this is why you most of the time will see this great circle curved as a curved shape. It was a couple of slides ago. Yeah, why do we see the great circle, which is the shortest route between point A to point B, as something which is curved and doesn't look as the short one? Yeah, because of the distortion caused by the Mercator projection. Because, for example, this picture is from the Google Earth. Yeah, from Czech Republic to Seattle. Yeah, this is the shortest distance, and it's curved. It's curved because this is the Mercator projection. And on Mercator projection, great circle is curved. However, in reality, it's not. But it's projection which is inadequate rather than real great circle. This is also Mercator projection. So that's why you have great circle curved and the wrong line straight. This, for example, picture is the it's from the website of some American airline, some charter airline, and they flew to Shanghai to some China, it doesn't matter. Yeah, it also shows the, like, it's not even the great circle, it's something somewhere in the middle, but it's representing yet just approximation of how the airplane flies. Yeah, and airplanes are flying great circles, which are short distances, but it's not represented here as the shortest distance, because again, this is the wrong type of the projection. So I hope now you get it. Why, for example, Google Earth draws you this arc when you select option direct to, yeah, from point A to point B, because Google Earth also utilizes Mercator projection. So what do we use in aviation, actually? In aviation, we use the third type. We use the conic projection. And there are two types of the conical projection, the simple cone and the secant cone. So first one is the simple cone. So you take the conical, you take the cone, you put it on the Earth, it gives you the tangent point somewhere at the latitude where you want to. You can select the size of this cone in a manner that it will perfectly fit the Earth in a pretty large variety of the latitudes. Yeah, of course, it will not touch it on the North Pole, and we don't need, because for the North Pole we have azimuthal projection, polar stereographic. It will also not touch it at the equator, but we also don't need this, because on the equator we have Mercator. But in a pretty wide range of latitudes, from almost equator to almost north, we can select the size of the cone, the angle of the cone that would touch the Earth at certain latitude. And this is how the charts are constructed, basically, by mathematical selection of the size of the cone, and then it touches certain latitude, and this is how the projection originates. However, it was the first idea, use the simple cone. Later on, we reconsidered our plans to use the simple cone, and we started using the secant cone because it's even more convenient, because it says that we already discussed that the chart will be correct at the point of the tangency. So where your figure that you are putting on the reduced Earth model is tangent to the Earth, there you will not have any distortion. So why don't we increase the amount of the points of the tangency? Yeah, by using the secant cone, which cuts through the Earth, so it touches the Earth, cuts through, and then goes out of the reduced size model of the Earth somewhere. You increase the amount of the point of the tangency. So here you have 2, for example, and actually maximum that you can have 2. But now between these points of tangency, you will have correct scale at this parallel of tangency and on this, and between them the error will be less. So it's more convenient because it gives you the less error. The parallels at which the reduced the cone cuts through and touches the reduced size models are called standard parallels. So this is how the chart is constructed. What? Okay. So yeah, if you will unfold first type of the simple, if you will unfold the simple cone, you will have the figure which looks like this one, which is already foldable, unfoldable figure, yeah, and but secant cone gives you even better result, yeah, because this is already looks like a map that we will use in aviation. So okay, secant cone contacting the surface at 2 parallels gives the less error. However, there is still some error. So the error is the following. Here's your cone and these are the standard parallels of the tangency. So between them, the scale contracts, and outside them, scale expands. But this contraction and expansion is so low. I mean, the expansion we don't cover. Normally, the charts are composed in a manner that your usable portion of the chart will be somewhere close to the parallel of tangencies, and in this blue area. So and because we can select the width and the angle of the cone, we can create such a cone that would perfectly, let's say, though its parallels of tangency would be exactly the size of the country, or less. So you will have very adequate representation of the scale of the country. And we don't have the uniform chart for the whole planet. Yeah, all the charts are divided by countries or sometimes by the regions. For example, in Czech Republic is one chart for the whole Czech Republic because it's small. In Austria, it's also one chart for the whole Austria because it's also relatively small. However, in US, you don't have the aeronautical chart of the United States. It would be impractical because it would be too big, and it also would be impractical because there would be a distortion. So you have the chart for each state, basically. So, and this type of the projection is called Lambert's conformal projection. It's this secant cone projection called Lambert's conformal. So this type of the projection is it's used in aviation. For VFR charts, that's as long you are not flying in polar region, you will use Lambert conformal. And in polar region, there is effectively nothing to navigate with. I mean, VFR at the North Pole, I don't think it's applicable at all. Yeah, ICAO Annex 4, this is the ICAO regulation that sets the requirements for the chart construction, says that the straight lines should approximate great circles, and actually it's really very close to, because the great circle, it will be always bended towards the I mean, we can omit this slide. It's not from the PPL. Because between those standard parallels, you will also have parallel of origin, which is calculated by the formula. But for simplicity, we may say that this is middle parallel between standard parallels, and it always will be concave to the parallel of the origin. But not a single PPL question asks this, where the great circle bends on the Lambert chart. So Lambert's conformal projection. Okay, here's the Austrian chart, and this Austrian chart we will use as the example to verify that indeed Lambert's conformal used for the chart construction, because it's written on every chart, yeah, on the top. Yeah, Lambert's conformal conic projection with the standard parallels 46 and 49 north. Then if you will take US chart, it's also would be written on top. Lambert conformal conical projection with standard parallels 25 degree, 20 minutes, and 30 degree, 40 minutes. So these are aeronautical charts. Now the scale of the chart. When the chart is drawn to scale, the relationship between measurements on the chart are exactly proportional to real world measurement it represents. So basically meaning that we have certain scale which can be represented as the ratio, it can be represented as the fraction, or as the units of the measurement. Let's say ratio and fraction are effectively the same, just the manner of how it's written changes. Yeah, ratio is 1 to 500,000, and fraction is also 1 to 500,000. It's just the manner. And units of the measurement, this is another type. 1 inch, let's say 20 nautical miles. So yeah, scale is exactly related to the distances on the chart. Of course, we will figure out now how exactly. So the scale of any chart, it's according to ICAO Annex 4. It should be written on any chart its scale, of course, because you need to know how many centimeters correspond to the actual distance on your chart. So what is this? Is this basically the scale is a relationship between the distance between map and the land. It's dimensionless. So let's say the scale of the chart 1 to 500,000, yeah, representative fraction 1 to 500,000, meaning that one map unit is equivalent to 500,000 lens units, and it's dimensional. So 1 centimeter equals to 500,000 centimeters on the land. 1 kilometer equals to 500,000 kilometers on the land, and one elbow is equal to 500,000 elbows, and so on. One pen, 500,000 pens, so on. How does it calculate it? The representative fraction calculates by dividing the chart length to the Earth distance. So, for example, here's the example. The distance between two airports is 220 nautical miles in reality. On the aeronautical navigation chart, the pilot measures 40.7 centimeters for this distance. What is the representative fraction of the chart? So, first of all, we need to convert everything to the 1 units. Since working with your aeronautical chart and using nautical miles is not handy, you don't have ruler marked in nautical miles. Yeah, you have ruler marked in centimeters or inches. You need what you need is to convert to one system, to the one denominator. Let's say, yeah. So 220 nautical miles, you will have to convert in centimeters if you are using centimetric ruler. 220 nautical miles is equal to 407 and something kilometers, because 1 nautical mile is equal 1.852 kilometers. Then 407.44 kilometers is equal 407,440 meters, because 1 kilometer is 1,000 meters. And then 407,440 meters is equal to 40,744,000 centimeters, because 1 meter is 100 centimeters. And so 40.7 centimeters on the chart equal to 40,744,000 centimeters on the Earth. So thus the representative fraction is 1 to 1 million. Yeah, because if you will divide both of those digits by 40.7, you will get roughly 1 to 1 million. So this is how the scale is calculated. Here's the conversion. Here's the list of the conversions between the values that we're gonna use, that we're gonna work with. You can take the picture of. Mostly we will work with nautical miles. However, because nautical miles is worldwide standard, it's for both Europe and US. But the thing is that measurement on the chart will differ. We use different rulers. In Europe, you guys would measure with the centimetric ruler. Guys in US with the ruler marked in inches. However, you still need to convert to the same units before you will derive the scale. And this is the formula how to calculate the scale. So Earth distance is equal scale denominator multiplied by the chart distance. Scale denominator, yeah, not like for example, 500,000, not 1 to 500,000, but denominator 500,000. You know how to work with this triangle, yeah? If you want to find this Earth distance, you need to multiply scale by chart distance. If you want to find scale denominator, you need to divide Earth distance by chart distance. If you want to find chart distance, you need to divide Earth distance by scale denominator. Yeah, and you need to convert everything to the same units. So you cannot divide centimeters to nautical miles. You divide centimeters to centimeters, inches to inches. As we did in our previous example. Yeah, we converted everything to the one unit.
During the flight planning exam, did we get a nautical mile ruler for the to measure the distance?
Can we use nautical mile ruler?
No. Yeah, so scaled rulers to measure the distance.
There is no. Okay, I got it. I got it. Yeah, you can. This is soon. There will be also on the slides. Yeah.
Okay.
However, the ruler itself is not noted in nautical miles. It's just the ruler is adjusted to the normal scale of the chart, which is normally 1 to 500,000. So about scale, we have large scale charts and small scale charts. Small scale, large scale charts will show you small area and more details, and large scale and small scale, large area and less details. So, for example, chart of the Earth would be the small scale chart because it will give you large area but very few details. Chart of the city, I mean, not used in aviation, both of them, but if would, then it would give you the very detailed representation of the city, but very few distance it would space it would cover. Now, let me just. How do we measure the distance on the chart? Some charts are giving us these distances basically already. If you will check this is the Jepsen chart. You will use this on your ATPL and guys in US CPL exams. Yeah, on this chart you have it's written on top. 1 inch is equal to 20 nautical miles. So you basically take the ruler marked in inches. Yeah, guys from Europe, you will also work with inches during your ATPL because Europe use Jepsen chart and Jepsen is American company. So inches you will also use. 1 inch and you measure 20 nautical miles. However, most of the charts, I mean, all the charts that I've seen before, use also this reference scale. Here, as you can see on the side. So you can take, if you don't have ruler marked in inches, you can take centimetric ruler, put it against this reference scale, and note how many, let's say you need to measure 50 nautical miles. Yeah, so you will check how many centimeters this 50 along the reference scale is, and then plot it against the chart. Or you will measure in centimeters the distance between those two navigational points and then plot against the reference scale, and you will derive your nautical mile distance. Because these Jepsen charts, they are not utilizing the scale as let's say VFR charts for Austria, Czech Republic, or even the US, where the scale is given as representative fraction, 1 to 500,000. However, for those charts which are utilizing scale as the representative fraction, 1 to 500,000, there also will be this reference scale below, because the scale is known. Yes, so why don't you provide this reference scale if the scale is known? Yeah, so this is how you can measure the distance between the points on the chart. Let's say between this Lima Juliet Bravo Oscar airport and this Lima Juliet Bravo Lim. You plot the ruler, measure the amount of the centimeter, then you put it against the reference scale. So this is one way how you can measure the distance on the chart, yeah, by using the reference scale. Another way is by using the scale. Yeah, for example, this is what we discussed before. Yeah, you measure the amount of the centimeters, then you know that you have a representative fraction of the chart is 1 to 500,000. So you use this formula, chart distance, 15 centimeters multiplied by scale denominator, 500,000. You will have how much? 50, something like 75 millions, yeah, and then 75 million centimeters. How much is? I'm not sure that I calculated correctly now, but whatever, you got the logic. Yeah, charts distance 15 centimeters by this scale denominator, you will get 7.5 million units, and you will 7.5 million centimeters, yeah, and you will convert how many those 7.5 million centimeters are in Earth's distance in nautical miles. Yeah, you will convert centimeters to the nautical miles. So that was the option number one. Option number two is to use this reference line. Option number three is to use the ruler, as Duncan said. Yeah, yeah. Apparently it was Duncan. That is noted in. Nautical miles and statute miles, yeah, and sometimes in kilometers, depending on conversion. Ah, okay, yeah.
You can also convert with the flight computer, can't you?
Yeah, you can do it without actually. I'll now show you how to do it without any means at all. With your finger, you can measure actually. This is actually sometimes it's thumb rule, yeah, because rule of thumb. So yeah, you can use the plotter, which is marked in miles and nautical miles. Just pay attention, statute miles, nautical miles, kilometers. Yeah, different plotters, different units of measurement. Just you need to. The only thing here is that you need to pay attention for is that the scale should correspond. Scale of the plotter should correspond to the scale of the chart. If the plotter have the scale 1 to 500,000, then you can use this on the chart, which has scale 1 to 500,000. If the plotter has scale 1 to 1 million, then you cannot use it at the chart with 1 to 500,000. It will give erroneous values. Some Pulis plotter, which are widely used in Europe, have both scales, 1 to 1 million for world aeronautical charts and 1 to 500,000 for normal VFR charts. So be careful. Okay, this is the example from the US chart, the same as we can see, also the reference line. Or another way how to measure this is the rule of the thumb, yeah, as Joanna said, which originates from the fact that we know the polar circumference of the Earth. Polar circumference of the Earth is approximately 21,600 kilometers. Now, we also know the circumference is like the whole length from North Pole to the North Pole via the South Pole. So this is the whole circumference, 360. Which means then that 180 would be, I mean, from North Pole to the South Pole would be half of this distance, 10,800. Which means that the distance from equator to pole, which is quarter, would be 5,400 nautical miles. And now we know that there is 90 degrees of latitude, yeah, because from pole to the equator is 90 degree, where North Pole is 90 and equator is 0. Which means that for each degree of the latitude along the longitude, each degree of latitude along the longitude, we have distance of 60 nautical miles as 5,400 divided by 90. Yeah. This is how it's visually calculated. And knowing this, we can now calculate any distance on the chart pretty precisely without a ruler, without the reference line, without the plotter. We just need to know this rule of thumb that each degree of latitude along the longitude is equal to 60 nautical miles. And since all the charts for airplane navigation must have this grid, I mean longitudes and latitudes depicted on it, you will for sure be able to next slide, I'll show you. Why we use only meridian for this? Why we don't use parallel of latitude for this? Because look how those parallel of latitudes look like. They are getting narrower and narrower up to the pole where it's not the parallel of latitude anymore, it's just the point. Yeah, so this trick cannot be done with, you cannot measure 1 degree along the parallel of the latitude because parallel of latitudes have different length. However, parallel of longitudes have always the same length because they are going from pole to pole. Yeah, it's just angle in respect to the Greenwich meridian, which is the only difference between them. It's just the angle. But the length of the line itself, the length of the meridian itself is always the same. But parallels are different story, parallels of latitude, because they are concentric poles which are shrinking to 1 point over the pole. So we don't use them. We use only vertical lines on the chart. So this is the Austrian chart, and it would have coordinates written on it. Here is your 49 and 48, for example. And we know that along the longitude, along the meridian, this distance is 60 nautical miles per each degree of change. So you can use this as the reference. You can use with with your hand, half like length from my elbow to my palm is 60 nautical miles. I mean, as an example. So half of that length is 30 nautical miles. Half of that length is 50 nautical miles. And following this logic, you can measure pretty much anything. But thanks God, you shouldn't, because even though you may not have ruler with you, there is no need to measure with, elbows. You can use something smaller. You can use, I don't know, the tip of the pen, which has some distinct color. For example, this in flight you will, for quick referencing, how many miles till this village? Okay, you just put it along the longitude. Okay, put it from your position to the village, and you can derive the distance. Why we can afford ourselves to measure so small distances with pen? Because the chart has graticle not only by the degrees, it also have more distinct graticle. So let's take a look on it. It's called the grid. Yeah. So this grid is not limited to degrees. So you may have chart with the grid of 1 minute, or you may have a chart with the grid of 10 minutes, or 1 degree, which is the rare case. Let's take a look. So you got it, yeah? So here's the big grid on the left. Smaller grid, smaller grid, smaller. Then within this small grid, you may have even more grid, and you can divide this grid endlessly, basically, and make it smaller, smaller, smaller. There's some logical limit beyond which your eye will not see this grid. So this is why, and plus it will make a chart hard to read. So this is why it's not gridded super in a super small fractions, but it's gridded enough for practical applications. So let's take, this is the closer look at this chart. So here you have latitude 47 and 30 minutes. So which stands for what? For 46 degree 30 minutes, yeah, because charts are oriented north up. All the charts are oriented north up. So the higher you go, the amount of the latitude will increase. So this is 46 degree 30 minutes, this is 47 degrees. So already we see that it covers the fractions of at least half of the degree, which is 30 minutes. But take a look closer and you will see that it's divided in terms in 3. Yeah, so we have grid, which is every 10 minutes, not every 30 minutes. But then even within this 10 minutes, we have smaller grid, which is already not cutting through the whole of the chart, but we have notches, these small notches. And these notches would be minutes. So basically your chart is gridded to minutes. Your VFR chart is basically gridded to minutes. So one more time, this is whole degree, and it's like half of the chart, yeah, whole degree. In this case, almost half of the chart. Then this degree is divided in half, then it's half divided in 3, and if you will look closer, you will have 1 by 1 notches, which are standing for 1 minutes. So if 1 degree is 60 nautical mile, then 1 minute is 1 nautical mile. So each of these notches represents you gives you 1 nautical mile. Again, I will say it can be done only along the vertical line. It cannot be done along latitude. Latitudes are on the chart. Latitudes are horizontal lines, yeah, of the grid, and meridians or parallels of longitudes are vertical lines. So it can be done only along the longitude, along the vertical line. And if you need to measure the chart, measure the length of on the chart, so you will just measure the amount of the centimeters, let's say from point A to point B, or not centimeters, you will put your, in flight, you will put your pen, okay, it's like almost whole pen between these two cities, maybe without this tip, yeah, without this tip. So, and then you just turn your pen, put it along the longitude on the chart, and count the amount of the minutes that this pen stands for. So here you have the big, this big grid sectors. This is 10 minutes, 10 minutes, and 1, 2, 3, 4, 5, 6, 7. So it's 27 nautical miles, yeah, because 2 by 10 and 7 of these notches. Yeah, this notch is also divided in a manner that you see the longer one stands for 5. So it's not written there 1, 2, 3, 4, 5. You need to count yourself. But the longer one, a bit longer one, is representing the middle of the square. And if your square is 10 minutes long, then it would be 5, of course. Clear? Okay, let's take 5 minutes, 7 minutes break. Don't mind, and we will continue. Okay. Okay. So let's continue then. Finally, moving to aeronautical charts, symbology. So symbology can be checked via there are different sources. So you can check it via VFR manual, aeronaut AIP for the European guys, and for the US guys, you have aeronautical charts user guide. So, for example, if you are from Europe, then you go to EASA unit briefing portal. On this briefing portal, we have AIP, we have VFR manual. For example, AIP. AIP section general 2, tables and codes. And here, 2.3, you will find chart symbols. That should work for any AIP within the Europe. Because for American AIP, you have aeronautical chart user guide. So they just relocated this to aeronautical chart user guide. If you are flying somewhere else in Europe, you can go to Euro AIP. We have AIPs of different countries. Let's say, for example, Austria. And then there will be the link. This link will take you to the digital AIP of Austria. So you go, current version, also general, 2.3 chart symbols. You see, it's everywhere the same. The structure is uniform. However, these charts are not enough most of the time for to operate with the VFR chart. So because of this, for VFR charts, they normally have own symbology on it. So in case of Czech chart, you will have it on the front side of the chart. So it's pretty much similar to that which you will find in tables and codes. I mean, different countries, they utilize slightly different logic. Let's say for Czech chart, most of the chart symbols will be found on the aeronautical chart. I mean, on the chart symbology section in AIP, because the chart is not available online. Then those symbols would be duplicated on the chart itself. But since the chart is not available online, they put all the charts to the AIP. For Austria, for example, where was our Austrian AIP? So for Austria, that would be slightly different story, because actually here also most of the symbols are located in the general 2.3 in the AIP, but with the different story with Austrian chart is that Austrian chart is available online in very high definition. So for this, you need to go to Austrian AIP, as we already show you where, and then on the same page where you have this AIP current edition, you will have also products, aeronautical chart, 1 to 500,000 scale. So you press on this, and you will have back and front section of the chart. On front, you will have normal VFR chart, which is identical to that which you're gonna use in your flights, with all the features that it has. However, there is also a backside of the chart available. And on the backside, you will be able to find all the symbology, which is applicable specifically to this chart. However, we can verify that still this symbology is very similar to what you will find in AIP. For example, church, the designator for the church is this circle with the cross on top, yeah? And in AIP, The same will be for church. Okay, the symbols are different between the countries. This is what I wanted to say, because if we would go to the Czech chart, they're not dramatically different, because there is a document that regulates chart symbology. This is ICAO Annex 3. Sorry, did I say Annex 3? Annex 4. Yeah, Annex 4. Annex 4. I remember. We will do it later. ICAO Annex 4. This document regulates what symbologies should be utilized for the chart. But if we will go through comparison, which we will not do now because we are kind of short of time, but symbols are a bit different from country to country, because ICAO is just the guidance. I mean, it's uniform document that says as it should be. However, it still leaves the space for maneuver for the countries, so they can do slight modifications. So, for example, those ruins can be shown in a different way. Let's say castles. You see castles and ruins. This is how they depicted on the Czech chart, and this is how they would be depicted on the Austrian chart. Like 3 dots. However, now currently also on Czech chart, they're also shown as the 3 dots. So those tiny details you will familiarize yourself more when you will get your chart and you will start flying. For the general familiarization, AIP is pretty much enough, depending on which country you are going to fly in. Refer to the symbology section of the AIP of your country, like for the state check preparation, yeah, for example. Then with US, for US guys in this case are the luckiest one, because you have the whole aeronautical chart user guide available, which where you will find excessive information about the chart itself and how to use them. Yeah, it can be found in Aeronautical Information Manual of the United States. This AIM chart, you go in Flight Planning Tools, AIM USA, and here just type guide. Nope. Aeronautical. Okay, aeronautical chart. User guide. Okay, user guide. You can type user guide, and it will be there will be a link, FAA Aeronautical Charts User Guide. Complete edition, and you will find all the possible and not possible symbology here, along how to use the chart, how to read this. So this is, you have, like, yeah, guys from US have really nice guidance of how to use the chart with examples, how it's calculated, like this elevation figure, maximum elevation figure on the chart, how it's calculated, where to look, how to read. So pretty much, yeah, extensive explanation. Okay. So this is about the symbology. Everyone understood where to find it? Either AIP General 2.3. I mean, my task here is to show you the possible amount of the information, the possible variety of the information that you may have on the exam, and of course there should be a component of the self-study. Of course, I we cannot go through the whole symbology of the chart for 3 hours. It's just not real. Maximum, I'm trying to give you maximum amount of the, at least where to look, you know, and what is the logic behind. So when you will do the self-study, regarding the whole symbols, I mean, you will, when you will fly with your chart, yeah, so when you will fly with your chart, I mean, when you will start flying, you will plot the route on your chart, and then you will check what are the symbols there, and you can always refer to your chart. Or when you are en route, you are see that you monitor in your position, you are performing the pilotage, and then you are reaching certain village, then there are some symbol next to this village. You can always revert to the backside of the aeronautical chart. This is why symbols are depicted on the aeronautical chart. For next week, next week we will go through different topics. Still, we will go through airspaces. Okay, so the stage 2 is next week. I didn't know when exactly the stage 2. On Monday we will have another class on airspaces, and the maximum information that is possible I'll give you, because what is the other plan? I mean, maybe you have a suggestion. Then what is your vision? Okay. So yeah, this is where to look for the symbology. Either AIP 3.2 or the Aeronautical Chart User Guide, or in case of Austria, you can or Austria backside of the chart. Then the charts itself. So among the symbology, there is also certain important things that we need to know about the chart. These are how the these are among the symbols, how we distinguish the build-up areas or cities and villages on the chart. So at all of the charts, it's per regulation from ICAO Annex 4. Large build-up areas are colored yellow with a black outline. And the shape of these outlines are identical to what you will gonna see under the night light illumination. So if the examiner or whoever it is will ask you what this yellow stands for, most of the time people answer these are cities and villages, but specifically these are visible patterns of the cities or the villages if you are flying in the airplane at night. So this is the element to promote your navigation. Yeah, so you will understand that you will be able to distinguish the city by the pattern of the lights. Also, we have the road, rivers, and railways, but these are from the symbology that you can find in AIP General 2.3 or VFR Chart User Guide. These can also be used as the means of the navigation. Then another properties of the chart, hypsometry. So hypsometry can be done in a different manner. So it's done. The reason for this is to show you the elevation of the terrain, because as the VFR pilot, you need to know whether you are flying towards the hill or not, or you can use it for navigation to identify the valleys and some, yeah, basically the valleys and hills, because this is about the elevation. Yeah, hypsometry is about the elevation. So, and methods of indicating of those elevation are the contour lines. They work in a manner as they do on the weather charts. Like the closely spaced isobar shows steep terrain, and the well-spaced contour lines isobar show the shallow terrain. So, for example, this is the example from the Czech aeronautical chart. Yeah, close to the border with the Poland, we have it's not mountains but rather high hills, and these high hills can be identified by the contour lines, as we can see here. The closer the lines, the steeper the terrain rise. Yeah. Well, technically, yes. No one restricts you. The thing over flying any mountains is the weather phenomena associated with mountains, and not only the mountain waves, but just normally in mountains, especially in summer, you have precipitations because you have uplift of the air, expansion, condensation, and precipitation. And in winter, there's generally the tops of the mountain are in clouds, because in winter, normally the stratus clouds prevailing, which are low layer clouds. So you can, but up to the referring to the circumstances. Yeah. So this hypsometry, not all the charts use the hypsometry because no problem, because it can quickly clutter the chart if you will have a lot of the lines which will interfere with the other information on the charts. So as the alternative to hypsometry, we sometimes use the layer thinning, which use different colors to depict different elevation. And you will have the legend on somewhere on the side of the chart how this layer thinning should be interpreted. For example, Austria used this layer thinning, US used this layer thinning, Czech use a kind of combination of hypsometry and layer thinning. We also sometimes use spot elevation. That would be on the other slide. Okay, this is how the layer thinning works on the IFR chart. Normally, IFR charts, I mean, just for general knowledge, it's not for VFR, but on IFR charts, there is no reason to clutter the chart. Yeah, so layer thinning is the less distortion, creates less distortion for your eye. But IFR charts, let's put aside. Spot heights. This is another type of the showing you the elevation. So, for example, this is the German VFR chart taken from the Jepsen, and here you have a lot of the elevation figures which are standing for the elevation of the terrain, yeah, above mean sea level, which is referred to the QNH. Yeah, so when you are flying on QNH, you can compare your altitude to the elevation of the symbols which you see on the features that you see on the chart, and then this is how you can guarantee yourself a vertical separation. And also, yeah, it accompanied with thinning a bit. So we have some hills. Some thinning is also applicable on this chart. So combination, yeah, it can be in that way, it can be that way, or the combination of that methods. Now this is, for example, from the USA. Okay, US is the great example of combination of all possible methods. So here we have contour lines, check, layer thinning, check, spot elevation, check, and also plus maximum elevation figure is also present here. Yeah, so how the maximum elevation figure is calculated, you can find in this chart user guide. Yeah, so there is a it's the figure for each quadrant of formed by latitude and longitude. One more time, the horizontal lines on the chart are latitudes, vertical are meridians or longitudes. So between they compose the grid. So within each sector of square of this grid, you will have this maximum elevation figure. There's some logic of how this maximum elevation figure is calculated. There are maximum elevation of the terrain itself, plus 100 feet for obstacle allowance, for plus 100 feet for man-made obstacle allowance. So there is the algorithm of calculation is explained in case you are interested. So this is the for the US guys, this is the altitude below which is unsafe to descend in this sector depicted on the chart. Especially, I mean, if you are in IMC. If you are VMC, yeah, you can of course fly adhering to normal rules. Yeah, 500 feet over the not populated areas and 1,000 over populated. But if you are an IMC, so this is the reference altitude that you shouldn't go lower to. So the charts, how do we check the chart validity from the practical perspective? Yeah, so because we know how to check the symbols now, where to find them, at least how to read the content of the chart, because there's hypsometry plus symbols already composing almost all of the chart. And now how to check the validity? Validity would be given in the aeronautical information circular. It cannot be found in AIP. You should go for the European guys to Aeronautical Information Manual, which is on the briefing page. Yeah, Aeronautical Information Manual, and then there will be the Aeronautical Information Circular, AIC, and you will press this AIC 2021 Aeronautical Chart. You will press on this aeronautical chart, and it will say that the current chart is from February 2021. So this is how to check for the Europe, for the Czech Republic. How to check for the US? For the US, validity of your chart can be checked from the. I have a link here. It's no, actually, where was? So on the same page, under Aeronautical Information Services Digital Products, you have VFR Charts section. You press on this VFR Chart section, and sectional aeronautical raster charts, current and the next edition date. So basically, this raster chart should be updated with the same rate as your normal chart. However, sorry guys, I never flew in US, but now I'm starting questioning myself whether this is correct, because 25th February, 22nd April, I mean, your charts most probably are not updated every month. VFR dates of latest editions for current and next effective. Okay, for current and next effective dates, see VFR dates and latest editions. So maybe it will be here. Yeah. Okay. Yeah. So it is. Dates of latest editions of aeronautical charts and related products. U.S. Department of Transportation and Federal Aviation Administration. Yeah. So for Europe, the charts are updated once per year normally. In EU, charts are made yearly at the end of. Yeah. So in Europe, they are updated once per year. In US, so when you will go to Aeronautical Information Manual, Aeronautical Information Services. So air traffic flight information, here is how to reach it. Yeah, you can type it though into this search bar. Yeah, the FAA site is done pretty well because you just type VFR charts, yeah, and it will give you VFR charts. You press on it and it gives you the same page basically. So sectional aeronautical charts. We use with sectional charts the charts because we have sectional, we have terminal area charts, but terminal area is the large scale charts for certain areas, let's say for TMA of certain airports. Yeah, and okay, so I'll activate attendance. So attendance is activated. And basically we're finishing, yeah, it's just yes, of course. Yeah, you need to just press on it and it will be, and that's it. So you just press on it and nothing else. So press on the button attendance, yeah. Okay, and the last, basically what I wanted to show you for today, and that will be rounding up, is the so the last thing that I wanted to show is the chart amendments. Yeah, so this is how we check the validity in terms of US. You have this table under the VFR chart section, yeah, the VFR dates of latest editions, and for where it's written for current and next effective days, see this link. In case of Czech Republic, it's Aeronautical Information Circular, and then also the rest, the last page for today is the chart amendments, because sometimes it happens that chart was issued and then there was no and then some area was added on the chart. However, it's impractical to reissue all the charts, to take all the charts from the use and issue the new version. So you will have the amendments, the corrections on the charts, to the charts, which are like all the subsequent amendments to the chart, which is already issued without renewing the chart itself. So for Europe, it can be found in AIP. You need to go to Aeronautical Information Publication, section 3.2, Aeronautical Charts, section 3, Services 3.2, and scroll down. Yeah, and scroll down. Till the end, there would be corrections to charts not contained in AIP. In AIP, you will find correction to the chart not contained in AIP. Okay, actually, there is some logic behind this name, but this is what you will have. So amendments to the chart. For the USA, that would be in section safety alerts and charting notices. So you just type safety alerts. No, maybe not like this. Maybe that's good if I would remember how to reach it by memory. So it should be in air traffic, flight and okay, alerts and notices. It's on top. Okay, air traffic. So FAA website, air traffic, flight information, and aeronautical information, aeronautical charts, alerts and notices, and safety alerts and charting notices. Yeah, so chart, supplement, publication, South Central. So you press on it, and there would be different notices regarding the VFR chart. Some of them are followed by some visual representation, like, for example, Bureau of Land Management, oil lease blocks, oil drilling platform, high density populated area is established somewhere. Yeah, and so on. Okay. So changes would be there. And for the tomorrow, attendance already says closed. Okay, and for the next time, we will go through the classes of the airspaces and how those airspaces are depicted on the chart, which airspaces we can go through, which we cannot go through, and how to identify their limits, vertical limits, their parameters, where to check for them in AIP, in FAA sources, and so on. Okay, so it says for me attendance remaining 8 minutes. Guys, if you let's do one task from the class charts and scale. Okay, let's do only first one, charts and scale. Try to open it if it works for you, and that would be it for today. Or if you want, we can do together. Let's do together. Okay, so Then look at the screen. Which projection is most commonly used for composing aeronautical charts? So secant cone Lambert's projection. That's correct. The nominal scale of the Lambert conformal conic secant cone projection is the scale at the standard parallels. Yeah, because we said where the okay, Jeremy, I don't know why it's not working for you. So yeah, where the chart is tangent, where the projection is tangent to the reduced Earth model, there we have the correct scale. That's correct. So that's why on azimuthal we have on the pole, Mercator on the equator, and the secant cone at the standard parallels where the cone cuts through the Earth. The shortest distance between 2 points is represented by great circle, of course. And the distance corresponds to 1 degree difference in latitude along any degree of longitude is 60 nautical miles. Sure, 1 degree. Yeah, 1 degree, 60 nautical miles. And then on a Lambert conformal chart, the distance between latitudes 1 degree apart along longitude 007 degree east is 5 centimeters. The scale of that parallel, scale of the chart at that parallel approximates. So this is, let's draw, because there is some misleading information in this question, intentionally misleading information. Okay, so we have 1 degree apart along longitude 007. So let's say this is our, okay, this is too thick. So this is our Earth. This is the prime meridian, and 007 east. So this direction is to the east. Yeah, if we look from the prime meridian side, this direction to the west. 007 east would be somewhere here. What's wrong with this? So somewhere here. Actually, it will go like this. Yeah, 1 degree apart along longitude. So this is the longitude. Along this longitude means here we have some parallels of latitude. And along the longitude, so like this, I cannot scale, unfortunately, more because my screen is divided. So like this. Got it, yeah? Let's draw here. So along this distance. 1 degree apart. So in this case, the longitude 007 east is irrelevant because any longitude, this 0007, the prime meridian, the 007 west, and all of them will have the same distance along 1 degree. It's always 60 nautical miles. So it's fair enough then to say that we measured this distance. It's 5 centimeters. Yeah, so 5 centimeters is equal 1 degree. And we know that 1 degree is equal 60 nautical miles. And consequently, 5 centimeters is equal to 60 nautical miles. Now we need to find the scale. Before we will find the scale, we need to convert 60 nautical miles to centimeters, yeah, because we need to work with the same units. So let's convert 60 nautical miles to centimeters. First is to convert from the nautical miles to the kilometers. Yeah, so nautical miles to kilometers. That would be 60 multiplied by 1.852. Yeah, because 1 kilometer is equal to 1 nautical mile is equal to 1.852 kilometers. So 60 multiplied by 1.852, that gives us the distance of 11 kilometers, 111.12 kilometers. Now we need to convert kilometers to the centimeters. Yeah, so we first need to multiply by 1000, which will give us meters. Yeah, so it will be 111,120 meters, or we need to multiply by another 100 in order to get centimeters, which will give us 100. Okay, we just need to add 2 zeros basically here. Yeah, so this is the amount of the centimeters. Yeah, 11,112,000 centimeters. So 5 centimeters on the chart is equal to 11,120 centimeters. So now we need to find the scale. So we can basically divide both of the parts of the equation by 5 in order to get proportion 1 is equal to. Yeah, so 1 centimeter on the chart relates to amount of the centimeters of the Earth in a proportion of 1 to 2,222,400. So this is your scale of the chart. Now you clear? Or we can use this formula from that I gave you. Scale denominator, Earth distance. So we need to find scale denominator. So we need to take Earth distance, which in our case would be 11,112,000, and divide by, but this is actually what we did, and divide by the chart distance, which is 5. Divide by 5, which give you scale denominator 222,000 to 2,222,000. Yeah, so let's check the closest answer is 2,200,000. Guys, clear? How does this how it's calculated? Anyone have questions? Please ask. It's no problem. I can put it and understand. I will. Okay. If for guys who works from the inches, you will just have to convert nautical miles to the inches. Yeah, because here's given 5 centimeters or 2 inches. Yeah, roughly. So 2 inches, you need to convert 60 nautical miles because 1 degree along the longitude is still 60 nautical miles. Yeah, doesn't matter whether you are in US or not. So it's still 60 nautical miles. You need to convert 60 nautical miles to amount of the inches, and then divide it by 2. Yeah, because 2 inches on the chart. Following this, John, take the one more time the picture of this equation, and just don't forget to convert to the same units. Yeah, nautical miles to inches by using this conversion logic. Okay, guys. In this case, that's all for today. Sure. No problem. Thank you, Jana. Thank you, Anna. Thank you, Alexander. No problem, guys. You're welcome. Mm. Thank you. Thank you, guys. Thank you, Samuel. So see you on Monday then. Jeremy, I hope that will be better than you than you expect. Спасибо, Никита. Работаем. Всегда. Ciao, guys.